of galvanometer into ammeter and voltmeter. So this was the only topic that was left from your magnetics, and then we have to start with chapter 5th. So what is a galvanometer that we have discussed already? That it's basically it's a device which is used to detect current in your circuit. Like it's either going to tell you yes, current is existing in your circuit, or it's going to tell no, there is no current in the circuit. Principle behind is that the current carrying torque which is placed in the magnetic field experiences a torque, and that torque tends to rotate the pointer due to the radial magnetic fields which are present. And construction was also over. Yeah, construction was also done. Now, torque we have already studied in our previous class. So there's a deflecting torque, means the torque with the help of which the pointer is being rotated. Okay, so with the help of which the pointer is being rotated. So that is the deflecting torque. So what was the formula of the deflecting torque which we have studied? It is NAIB. N was the N were the number of turns. N was the number of turns. AIB, area, current, magnetic. This is what we've already studied. Then we have the restoring torque. One more torque we have, which is the restoring torque. What is the restoring torque? Rotating, deflecting torque is the torque by which the point is the torque. See, for torque, for equilibrium, we have always seen that if one device rotates, then another torque is present to align it back. If this pointer is rotating, then there is another pointer which is present to line it back. Okay, that is known as the restoring torque. This is equal to k theta. Now we can equate both the torques. So it is NAIB is equal to k theta. So what is theta from here? Now, why restoring torque is equal to k theta? This is a concept from your class 11th portion. Okay, this is a concept from your class 11th portion. How? Firstly, the force which is present in linear case, it is equal to minus k. So this says that the force which is present is directly proportional to the displacement from the center, from the mean position. Then negative sign is showing the direction which is pointing away. And k is the spring factor. We have revised it in this batch also. And you already have studied this portion in your class 11, waves and oscillations, waves and SH. So this is the linear displacement. This is the linear displacement. Okay. So it means this is valid in case of linear motion. Now, if you have rotational motion, then that also we have studied. Remember torque's condition. This is not new. We have already done one question based on this. So the rotational motion portion is this. Okay. The rotational motion portion, basically we have covered it in circular motion. This is the same portion. So torque, now force becomes torque. This becomes minus k of theta. So this is from your concept of waves and SHM. So those who do not remember it, those who want to revise it, let me know. I can arrange a class also if you want. So here we have the value of theta. Theta is equal to NAIB divided by this K, which is produced. Whatever is the angular deflection that is produced, that is known as theta, means it is the angular deflection. That is angular displacement. It is basically the angular displacement. If the pointer is like this and displacement is being occurred. So here the pointer is actually displacing it in terms of angle only. Yes. Look, like this. So the pointer is moving, but here it is at the center where it is subtended at the soft core. There it is subtending and making an angle itself. No? So basically, it's the angle that is being swept by the point. Okay. So what is theta? Theta is the angular deflection. Now here we have a name for this K. This is theta, and this K, this is called torsional factor. Okay, or basically torsion constant we say. We use the term torsion constant. So basically we have a concept of spring factor. Spring factor, which is represented by the K in our equation, F is equal to Kx, this K. This is actually a spring factor, means this is not very specific. If we are talking about specificity, this is not very specific. As in, for every material, for any device, for every device, it keeps on changing. Okay, it will be changing. Like if I say spring mass system. So for spring mass system, the value of K is 2 pi. That's why we use the equation T is equal to 2 pi under root L by G. Correct. So K is equal to 2 pi is a constant. When we are talking about just spring block system, that is spring length of a spring, that is spring and a bob, string and a bob. So for strings, we use this. If we have spring mass system, this is present. Then this is called spring constant. This is called spring constant. So basically what I mean is that spring factor is a general term. This K is not spring constant. Spring constant is particularly for your spring mass system. It is not for any other. And for every other device which is present, for every other system which is existing, you already have certain constants. That has to be followed. Okay. So this is what is meant by theta. Okay, sensitivity we'll do later. First, write down this page. Okay, class. Now let's come to the sensitivity part. So what is meant by sensitivity? No, now the normal term sensitive you already, right? That's a normal common word in English we have been using. So when we say a particular person is sensitive, so what is the meaning of that? When you use this person is very sensitive, we use this term, right? So that basically we use if we say very small things and we have not said a huge thing or a thing which can hurt someone and the person reacts to it. And so the person is very sensitive, right? So same thing is the case of galvanometer. If you give a very small amount of current, the galvanometer is able to detect it and shows a large amount of deflection. So this is the same case. You say you go and you tell your friend something for correction, something for improvement, just something like that. And the person reacts to it. So what do we say? We say the person is very sensitive. So same thing. Small amount of current, huge detection. That is huge deflection. That is the same thing as sensitive. So if the galvanometer is able to detect small values of huge current, or small values of current, means huge deflection. So there are two types of sensitivities which are available. There are, firstly, we have current sensitivity is present, and then we have the voltage sensitivity. So what is meant by current sensitivity? Current sensitivity is particularly related to your current. That is, you have a deflection which is present. Deflection is being done. That is, it is showing you that yes, a small amount of current is present. But that is not letting us know the exact value. Like see if I'm getting a huge deflection for a particular value of current, so my judgment will be that this entire circuit which I have plotted has a large amount of current. So it means there's a problem in my calculation or there's a problem in the galvanometer. If there's a problem in my calculation, that's a different. That means it's a calculation error that we get in the circuits while we are working. When you were in class 11, you must have studied error. No, now it's related. Error analysis was the portion where we used to study these things earlier. But if it's the problem of the galvanometer, if it's the issue, if it's the problem of the galvanometer, then it means our circuit's calculation can never be precise. Why? Because we have constructed the proper circuit. Our circuit is proper, our circuit is normal. But the result which it is showing and which it is supposed to show, these are completely different. So that's the case. But in simple terms, you can understand simply deflection. What is deflection? NAIB by K divided by I. So current gets cancelled. So current sensitivity is equal to NAB divided by K. So what it is? Deflection per unit current. Same thing for voltage. Now theta, what is V using Ohm's law? It is equal to IR. And what is theta? Theta is equal to NAB by, what is theta by I? Theta by I is current sensitivity, which is NAB by K. So NAB by K. By theta by I, if you notice here, this theta by I, this is the current sensitivity. So this divided by R gives us deflection per unit voltage. So these are the two types of sensitivities which you should write down this portion also. Then we'll start with the first one. Okay, and now look, the first device that we have is the ammeter. So what is the function of the ammeter? Firstly, we have to understand what is the function of the ammeter. So ammeter is basically present to get the value of current. Now, when we were studying galvanometer, what did the galvanometer do? It just told us, or it just tells us that the current is present or not. How much current is present, whether according to the deflection, you can just have an idea that the current is large or the magnitude of current is small. But if I want the precise value, if I have two values, 2 milliamperes and 3 amperes. So for 3 amperes, I'll get a huge amount of deflection. But for the smaller one, 2 microamperes, I'll get a smaller deflection. So this way the galvanometer works fine. But what if I want to calculate the value? It means I am using my galvanometer and the circuit. I am forming the entire setup as an ammeter. Conversion of galvanometer into ammeter is not something like we are changing the construction of it from the code. That I'm inserting a device and making it into ammeter and how to transform it. No, it's actually if I just have a galvanometer and if the circuit is present, I just have the galvanometer and the galvanometer is just detecting whether the current is present or not. Then how will I be able to calculate the value using this setup? I'll give you a wire, I'll give you a resistor, I'll give you the galvanometer, switches, keys, all these are present. Construct the circuit and tell me exact value of current. You'll not be able to do by just looking at the galvanometer scale, by just looking at the pointer, you'll not be able to. So for that purpose, what do? We connect, this is very important that we connect the resistor which also has been provided to you. That in parallel with the galvanometer. Like, see, this is the wire. Wire has this resistor. Resistor is further connected to this wire. So current is coming. Some amount of current is going towards the galvanometer. Whichever amount is now left is going in the second wire. So branching has occurred. We have studied, especially Taha and Supian. You also now must be understanding this portion that how when the current comes, it gets divided. Okay, so one is Ig, another is I minus Ig. Yes, this is clear. Mariam, Khatija,
Yes,
Siddiqa.
ma'am.
Yes, ma'am.
Okay. Now, see, shunt is present. Shunt means the exact resistor which is present. Now, the resistance, we are assuming that it is S. S variable, it's just a variable to differentiate the rest of amount of current. This resistance for this galvanometer is capital G. Okay. Ig is the current through the galvanometer. So everything has been written. Resistance of the galvanometer, shunt resistant, current which is flowing through the galvanometer. Yes, one more thing, the value of this shunt, this is very small. It's a small resistance which is connected. Small resistance and which is connected in parallel. This is connected in parallel. These are the two conditions. If you remember them, you can easily figure it out. How? Shunt and galvanometer. Both the resistors are connected in parallel. Now the entire theory of the parallel concept will come. Potential difference across galvanometer. What is the potential difference across the galvanometer? IR, current is Ig, resistance is capital G. So this is Ig into G. What is the potential difference across the shunt? I minus Ig into S. Into S. So how can we calculate the value of the shunt? Shunt will be equal to Ig into capital G divided by I minus Ig. So this is how we calculate the value of the resistor which is missing. So everything can be calculated. If we know now from here, I can be calculated, from here, Ig can be calculated. If whichever is given and whichever is missing, you can calculate. This is how we write it down, then we'll come to voltmeter. Okay. Then next one, let's see how to convert it into a voltmeter. So again, you have the resistor, you have the galvanometer. Now a high resistance, see this is of a higher magnitude. So high resistance, you are going to connect in series. Okay. So this is a straight wire, galvanometer is present by a resistor, and again a current is going this. On single current E into R. Now what is the resistance? G plus R. G plus R. So G plus R is equal to V divided by IG. What is the value of this resistance? Because when you know the value of the resistance, then only you're able to calculate anything which is mentioned. So this is V by IG minus, that's it. One question, let's see. Or you tell me the answers first. The first part at least, second part I'll tell you. Write this down first, then try that question and submit your answers in the chat column. No, I've just said, Taha, that write down this first, then the question when I'll show you all. So then submit your answers first for the first part. See, the last question that we have is an ammeter of resistance 0.8 ohms. This can measure currents up to 1 amperes. Now, what must be the shunt? So we have to find out the value of shunt to enable the ammeter to measure current up to 5 amperes. So what is this? This is the value of the shunt resistance we have to find out. Ammeter of resistance 0.8, shunt resistance we have to find out. So yes, we have already seen the formula here. This one we are going to use. S is equal to Ig into G divided by I minus Ig. Okay, now we have to find out the shunt resistance. This is saying ammeter of resistance. Now our ammeter is this galvanometer and its current is 1. So it means Ig is 1. This is 0.8 divided by 5 minus 1. So this is 0.8 divided by 4. This is 0.2 ohms. Second is, what is the combined resistance of ammeter and shunt? Shunt is there 0.2 ohms. Galvanometer is there. Ammeter is what our galvanometer only. That's why we are using 0.8. Now combined resistance. We know they are connected in parallel. So their R equivalent will be S into G divided by S plus G. So this is 0.2 into 0.8 divided by 0.2 plus 0. Okay. So this is 16, 0.16, and this is 1. So this is 0.16. Write it. Question all of you have written, or anyone wants to see the question?
Ma'am, I want to see the question. I have the last part left.
I'll show you. So this completes with the chapter also. Let me start with the 5th one. First, write it down. Take your time, write it down, then I discuss. See now we'll be starting with the fifth chapter. Now fifth, sixth, seventh, eighth. These are very short chapters. That's why I invested so much time in the first four chapters, because the first four chapters are really important and really lengthy and have so many concepts in it. Now, if you are clear with the first four chapters, then you are able to understand the fifth, sixth, seventh, eighth. Even eighth is very small. It just takes 2 classes. That also I discuss it in 2 classes. It's just possible in 1 class. Because in this chapter fifth and the EM waves chapter, you have a huge table which you have to rote learn it by yourself. There I cannot help. Ferromagnetic क्या होता है, ferry these diamagnetic, paramagnetic, all these you have to learn. Similarly, EM's waves maybe you have a huge table. So कौन सी waves क्या show करती हैं, that you also have to remember. So all these things are there for just rote learning, which you have to rote learn, and as it is you have to copy it in your exam. So वो खुद कर लेना सब. That data I'll be sharing and I'll be discussing everything, but it means you have to, that portion requires your effort more than our class discussion. We'll be discussing, in fact, I'll be giving you short tables. So learn it from there, it will become easy for you. On WhatsApp, Learnivio will share it with all of you, so that from there you can learn. But before that, we have certain details, and here in this chapter, we have certain things to be discussed. So now the syllabus has to go a little fast, okay, class? So till fourth chapter, I have gone very slow. So till the fifth chapter, we have to discuss everything quickly. Now, extra classes will also be scheduled, because your exams are coming and some students are having sixth chapter also. So that also has to be discussed. And I think Khadija or someone is having AC also. We have to discuss that. So what is chapter fifth? This is magnetism. So magnetism, we'll be discussing it in detail, and matter. So the types of matters which are available, that portion has to be dealt by you a little. So be prepared. That portion is boring also. So you have to learn it, and we cannot help that. You have to learn it. So we deal with the magnets, the natural magnets which are present. Natural magnet, the best example is Earth. And permanent magnets means the artificial magnets which are available. Like you have the best example of the bar magnets. So we have a huge discussion of bar magnet first, then in the later section, we'll see the Earth as a magnet. So what is a bar magnet? It is an artificial magnet, firstly. You have seen it's a bar which is present and it has two polarities, both the polarities north. This you know, I hope you know about the polarities. It's north and it's south. This we'll be discussing in the next segment, which is about the properties. So north and south. Now the first property. All these are very basic concepts from your lower classes. Attractive property, you know, when north and south are brought together, they'll be attracting. So opposite polarities have this. If you bring north and north together, or south and south together, it will be repel. Then it means it has a directive property. Directive property means okay. So you have this, and a bar magnet is there, and this is stuck like this. Is it is freely suspended. So after a while, what you will notice, automatically it has aligned itself in north south direction. So that is a directive property. Then magnetic monopoles do not exist. You can have You can have plus Q existing, you can have minus Q existing, but you can never have North Pole or South Pole existing. This is not possible. This is possible. Even if I take a magnet, North, South, I cut it. Means now I have this end as North and now I have this end as South. But this doesn't happen. The other side which is left, this develops South. The opposite side develops North. Last property, magnetic induction. It means if I have a magnet, I have a bar magnet, let's say this is a bar magnet, and I have a material like that of iron. Suppose I have an iron ball which is present. The best example is the iron ball. And I keep on rubbing it over the magnet. So after a time, I will see that the iron ball temporarily is having the magnetic properties. So these are very basic properties. Write it and let me know if you have any queries.